Hey guys, in the previous video, we did talk about the F-test and how we use the F-test to compare population variances, right? So here, remember in your t-test or whenever you do two-sample t-test, it is the assumptions for those t-tests are the population standard deviations are similar. So how do you know or how to test if the population standard deviation or the population variances are similar between two samples? Well, you could use the F-test to actually compare that, where the null hypothesis would be the sigma 1 squared minus sigma 2 squared is equal to 0. That means the population variances are identical. And the alternate hypothesis being that the variances are not identical and they're different from 0. Okay, so you could change these hypotheses to say if they're greater than 0 or less than 0 and so on. So, but you could to convert this two-tail test into a one-tail test if you want. Okay, so but this F-test has other functions. So far in your t-test or your z-test in some sense over here, we just looked at one sample or two sample tests. So what if you want to actually compare more than two samples? Like, if the samples of three different samples or four different samples are actually similar. Let's look at an example where, let's say, A, B, C, D, and where you're looking at weight loss treatments, and you want to try and figure out if there's a better way, if certain kinds of exercises result in better weight loss. And A is walking and swimming and biking and dancing. If any one method is similar or are they all similar, and weight loss is just related to calories in versus calories out, right? So if you need to do a t-test to compare these four different treatment methods, you would need to do 6 different treatments, right? So it's A, B, A, C, A, B, B, C, B, D, and then finally CD. So you need to compare the t-tests for 6 times if you want to answer the question, are these 4 methods similar or are they different in some sense? So if your alpha, which is the typical alpha, the level of significance we use is a 5% cutoff, that means the probability of a type 1 error that you reaching the wrong conclusion is going to be only 5%. And 95% of the times you will have the right value. But the probability of all 6 of these t-tests being correct is going to be 6 multiplied by 0.95, and that is going to be only 0.735. That means only 73.5% of the times you will have all 6 t-tests correct, and 26.5% of the times you will reach the wrong inference in some sense. And this high probability of type 1 error is kind of not acceptable. And another way to try and figure out if these means are actually similar is to try and use the F-test, right? So the F-test, in addition to checking if population variances are similar, can also be used to check through those variances, through estimates of variances, to check if groups of samples, if sample means are similar or dissimilar. Okay, so the way that happens for hypothesis testing in terms of F distribution is it's based on the idea that the total variation in the sample is equal to the treatment variation plus some sort of random variation. So we will get to this part a little bit later. And again, remember, the F-test can be used to figure out the null hypothesis under F-test is going to be, say, the 4 sample means are similar. mu1 is the same equal to mu2 is equal to mu3 and is equal to mu4. And the alternate hypothesis that they are not all equal. So this is the alternate hypothesis for F-test, where you could try and figure out if groups of mean are similar or they are dissimilar. So this is typically the same hypothesis for most F-tests when you're comparing multiple samples and trying to figure out their means. Okay, so what the actual F-test in some sense is going to be is the estimate of the population variance between different sample means or among the sample means. So in our example, that is going to be between, let's take the means of walking, swimming, biking, and dancing. So it's going to be the differences in the variance. We are going to try and estimate the population variance between these groups divided by the estimate of the population variance based on the variation within each group. So you're going to look at variances between each group and then variances within each group. And based on these population estimation variances, you will find out this F test value. And this will give you the critical value of F. Okay, so if this critical value, if it's somewhat close to 1, right? So not the critical value. If this F value is somewhat close to 1, that means they are all similar. And if this ratio is actually different from 1, then you could conclude that they are all not equal. There's the population standard deviations are somewhat different. That means the means of these groups are different. So this is an example. Let's go through a simple example of airlines in some sense. So a lot of airlines, this is an example where airlines have cut services and they've cut meals and snacks and so on. So their marketing survey research, they went and found out the level of satisfaction, and they surveyed a bunch of passengers with different airlines. And you have 4 different airlines, and you have Airwaves, Bel Air, Cirrus Airlines, and Debonair. And these are the satisfaction scores. And they randomly selected a few passengers, 4 from Airwaves, 5 from here, 6 or 7, 7, and then 6 over here. So this is the 5-step hypothesis testing procedure which you will be using. The first step, we kind of wrote that down already. The means are similar, and the alternate hypothesis being that the means are not equal. Standard, you determine the level of significance. Typically, we use it at 5%. We can go to 10 or 1% sometimes. We're going to use F distribution. The decision rule, in some sense, is going to be using the F statistic. The decision rule is that if the F statistic which you find out is greater than the critical value, that means the means are not equal. If the F distribution is like less than the critical value, that means they are similar. That's how you would design. But in order to do this, we will need to use the degrees of freedom. And as you remember, the F distribution has 2 degrees of freedom, the degrees of freedom for the numerator and the degrees of freedom for the denominator. The degrees of freedom for the numerator is the number of groups minus 1. So K groups, here in our example, we will be using 4 groups, and here as well, 4 groups, 4 airlines. So K minus 1, and that would be the degrees of freedom, the numerator. And the denominator is within each sample in some sense. The denominator is N minus K. Okay, so total number of observations minus the number of groups. So here the total number of observations are 4 plus 5 plus 7 plus 6. What's that? 9 plus 7, 16, 16 plus 6, 22. There are 22 observations here, and there are 4 groups. So it's going to be 22 minus 4, that is 18, and that is the denominator. And once you have this, you need to create this table, which is known as your ANOVA table. ANOVA stands for Analysis of Variance. And this table, it's nice to know how to create them, and your software package will create them for you as well if you're using Excel, which I highly recommend to work out your F statistics. But it's nice to know how to do it by hand as well. So the first thing which we talked about over here, your total variation among all a total variation is this variance of the whole sample in some sense. So here it would be taking all 40 observations and just finding out the variance of this sample. That's your total variation. This total variation of all the observations put together is going to be the treatment variation plus the random variation, right? So the first one, you find out the sum of squares for the treatments. And the second part is you find out the sum of squares for the errors. And once you have these 2 values, you find out the mean square for treatments and the mean square for the errors, dividing it by the degrees of freedom. And once you have the MST and MSE, the F statistic is the mean square for the treatments divided by the mean square for the error. So this MST and MSE are the same as this formula. So MST is the estimation of population variance among different sample means or among different treatments or among different groups. And the MSE is the mean square error, or which is the estimation of population variance based on variation within each sample. So how do we do that? Well, let's go ahead and actually look at what they are actually. So the overall sum of squares total is x minus xg, where g is the overall grand mean. That's just the variance of the overall population, which here is the variance of these 22 observations. You find the overall mean, and that will give you the sum of squares for the overall total. And the overall, the sum of squared errors for within each group is, let's take the average for these 4 observations. And the average for those 4 observations is going to be, let's look at the value, 94, 90, 85, and 80. So these are the 4 observations for air waves, and the mean is going to be 87.25. So the deviation x minus mu or xc is going to be 94 minus the mean. And so these are the deviations, and then you could square them. And these would be the mean squares for each of them. And once you square them, you could sum them up. So that's be the sum of squares, summation of sum of squares for each group, right? So once you find out the sum of squares for each of these groups, so these are the sum of squares for the first group, which is airwaves. And similarly, you could do the sum of squares for the second group, and the third group, and so on. So, and once you find out the sum of squares for each of these 4 groups, so this is going to be, okay, this is 110.75. Value. Sum of squares for error here. Detailed calculation, that's for error. 94 minus 95.64 square, 18.36 square. Oh, that's a grand mean. Yeah, 110.75. There you go. So that's the value which we actually looked at. We found out for airwaves. And similarly, you could find out these differences in sum of square deviation. These are the square deviation values. And you find out the square deviations for each of these groups. And once you find out the square deviations for each of these groups, that is going to be the 594.41. And so you have these 2 values, the overall sum of squares of the total and the sum of squares of error. And once you find that out, you could find out the sum of squares for the treatment by just subtracting the random variation from the total variation, and that will give you your treatment variation, which is a much faster method in order to calculate your SSTs. You could also calculate them in person, but this is a much straightforward way which you could calculate the sum of squares for the treatment. So this is your sum of square for the treatment, the sum of squares for your errors, and once you find that out, the degrees of freedom for the numerator is 3 and denominator is 18. You find out the mean squares, and your F statistic is 8.99, right? So how do we know if this F statistic, if the means are different? Well, let's actually go and look at the critical value of F. So the numerator is 3 and denominator is 18. So this is your table, appendix B7, and this gives you the critical values of your F distribution. So the numerator has 3 degrees of freedom here, and the denominator has 18 degrees of freedom over here. And so that would give you a critical value of 5.09. So 5.09 is your critical value, it's your critical F value in some sense. And here your value is 8.99, and well, I'm not sure why this says the critical value is 3.16. It's 3 and 18. 3, 18. These are my critical, I'm getting a critical value of 5.09 from, this is 1% level, so that's fine. At the 5% level of significance, we get 3 and 18, which is 3.16. So your F statistic 8.99 is greater than 3.16. So even if you're using the 1% significance level, it is still greater than 5.09. That's a critical value of F at the 1% level. That means you reject the null hypothesis and the alternate hypothesis is understood. That means the means are not the same for all of these 4 airlines. The customer satisfaction actually differs for these 4 airlines, and the means are not the same. Even by eyeballing them, you could kind of figure out. Look at for Debonair Airlines, these are in 60s and 70s, whereas for Airways it's in the 90s, and these have a little more variation. So you can tell that the means are not similar across variations. So that's the only thing which you could actually find out using F-test. So F-test does not tell you that Airwaves is better than Cirrus or Bel Air is better than Airwaves and Bel Air is better than Debonair Airlines. No. The only thing F-test does here, when you have more than 2 samples, it can tell you whether they are similar to each other or if they are not similar to each other, in the sense of that are their means equal or their means unequal. That's all the F-test can tell you. So once you have this sort of comparison, when you want to compare the means, if they're similar or not, if you find out they're not similar, then you could go for additional tests. And that is the F-test. And I will be posting another video using a different example using Excel. And that'll be the next video.